Hello everyone, I am Patrice Desvallées from DGAC, the French Civil Aviation Authority. I am very honored to make this IAC21 presentation called At Crossroads of Aeronautics and Space, with co-authors from Dassault Aviation, Ariane Group and ONERA. We are going to display on a single graph all the main categories of aerospace systems, considering their velocities and altitudes from the ground up to 36,000 kilometers. A third key metric will then be introduced, embedded energy. Our planet has a deep gravity well and a thick atmosphere. However, the world aerospace sector made the best of it and managed to produce since World War II a wide range of diverse and ultra-high performance flying systems. Aerospace still is a very rich and dynamic sector as it continues to develop and evolve rapidly. It now covers a wide range of diverse projects. Today, some emerging innovative systems, like suborbital vehicles, are raising the issue of the lack in international law of an explicit delimitation between the sovereign airspaces and the outer space, the latter being accessible to all for peaceful use. There are indeed two somewhat diverging legal regimes with respect to the sovereignty and jurisdictions of states above their territories. Could a functionalist approach and/or an energy metric unravel this issue? A good way to understand this fast evolution is to represent within a single logarithmic scale diagram all the main aerospace categories using key parameters. Altitude from ground up to 35,800 kilometers and speed from 0 up to 28 kilometers per second. Also, the embedded energy, a metric combining both altitude and speed, is a very meaningful third parameter for our graph. On this slide, you can see the base frame for our graph. The two logarithmic scale for speed, x-axis, and altitude, y-axis. Also, some significant markers are indicated. For example, Mount Everest at 8.8 kilometers height, the stratosphere ceiling at around 50 kilometers, which also corresponds to the max theoretical buoyancy altitude for stratospheric balloons. The non-official 100 km Kármán line, or the typical speed of a rifle bullet at 1.3 km per second. Here we see more landmarks added to the graph. Some ISO-Mach curves, Mach 1, 3, 5 or Mach 10, hypoxia starting at around 2 km. Also, the ambient pressure decreases with altitude. The embedded mechanical energy, dubbed EE, equals to the sum of kinetic and potential energies divided by the mass. We trace some ISO embedded energy curves at 1, 10 or 40 megajoule per kilogram. For example, curve C at 1100 kilojoule per kilogram corresponds to the level above which vehicles are very likely to need thermal protection in order to survive re-entry heating. On this chart, point A is key. It represents the lowest circular Earth orbit at around 155 kilometers. That means that a non-propelled satellite at this altitude quickly experiences a significant orbital decay. The atmospheric drag will pull it in fast, after only a few 88 minutes full orbits. The corresponding embedded energy is 32 megajoule per kilogram. To be orbital, any object or vehicle needs to be above this 32 megajoule per kilogram energy threshold. This curve is dubbed O. The envelope of Earth's circular orbit is curve OC, going from point A at 155 kilometers up to the geostationary orbit. The H pink window indicates some typical orbital decay durations. For example, a 300 kilometer orbit lasts about 1 month, while at 900 kilometers, a passive object can remain orbital during 1,000 years or so. Now, here you can see from the upper right corner down to the left, ranked in energy descending order, the geostationary orbit at 57.8 megajoule per kilogram, the Galileo constellation at 55.8, a geostationary transfer orbit envelope at a constant 54 megajoule per kilogram from apogee to perigee. We also drawn typical asteroids entering the atmosphere with speeds from 12 up to a whopping 72 kilometers per second. Finally, we added envelopes of altitude speed data for two typical trajectories: a vertical two-stage launch to orbit and the space shuttle re-entering and landing. Et voilà, we now can place in the graph typical examples of aircraft, spacecraft and other aerospace systems, either existing programs, projects or future concepts. Each vehicle is plotted in speed and altitude at its point of highest embedded energy level reached during a typical nominal operation. The main aerospace categories can then be located from light and slow stratospheric aircraft, including apps like the CNES Scientific Strateol 2 balloons, the Stratobus airship, or the Airbus Zephyr S unmanned electric glider, to subsonic transport like piston-light aircraft DR400, helicopters, regional turboprop aircraft like the fuel-efficient ATR-42, up to the recent advanced material turbofan Airbus airliners and Falcon business jets. Then we have the supersonic transport category with Concorde and supersonic military jets. Some can fly up to flight level 660, about 20 kilometers. The potential future suborbital Earth-to-Earth transport, including near-orbital systems with speeds close to orbital velocity of 7.8 km per second. Then we have the much less energetic local A2A suborbital category with zero velocity at apogee. Typical apogees would be around 105 or 110 kilometers, while some systems aim lower at around 85 kilometers. Future flights at $200,000 per passenger should provide 3 minutes of weightlessness while sensing the Earth's curvature. Finally, we have all the various orbital systems from LEO up to GEO. And now we have a completed graph providing a meaningful big picture of all aerospace categories around our planet. Here, embedded energy values are indicated for various machines. Robin DR400 light piston aircraft at 48 kJ per kilogram, ATR-72 turboprop at 86, Airbus A350 at 160, Dassault Aviation Falcon 7X business jet at 172 kJ per kilogram, Concorde at 354. Local A2A suborbital aircraft are slightly below 1100 kJ per kilogram. Earth-to-Earth suborbital systems from 28 up to 31 megajoule per kilogram for near-orbital transport. This is right below the lowest orbit energy at 32 megajoule per kilogram. Thus, local suborbital systems are 30 to 39 times less energetic than the lowest circular Earth orbit. Finally, lunar systems are around 60 megajoule per kilogram, and Mars-bound spacecraft likely between 70 and 100 megajoule per kilogram. We can identify a kind of corridor or gateway linking aviation and outer space. This gateway has a bottleneck shape in the middle around the near-orbital cluster and point A, which is the lowest Earth orbit at 155 km and 7.8 km per second velocity. Some main areas are delimited on this slide. Each area is generally specific in terms of technologies or usage. Some other areas don't have any use case or are impossible in the Earth's environment. We saw that suborbital systems are split into two categories: local A2A flights and the much more energetic Earth-to-Earth category. This could possibly develop in the next decades, and so should the issues of airspace disruptions and safety. Other important aspects include legal and regulatory issues, safety of the vehicles, of passengers, as well as third parties. Also medical, national security and sovereignty, types of propulsion and energy, environmental impact and sustainability, cost and technology readiness are key issues. Some of these nascent projects still need R&D to mature further. In a timely manner, a future safety regulatory framework should be adapted for the most promising and mature technologies. To conclude this presentation, this graph provides a meaningful big picture of the entire aerospace domain with a sense of scales. The anchoring physical limits for ranking the various aerospace systems is rather a matter of embedded energy than speed or altitude alone. Main aerospace categories are identified together with various limits, thresholds, interrelations or gateways between aviation and space. Finally, the ambition of the authors in making this chart widely available also is to provide a standalone tool that could help all private and public stakeholders interested in ultra-high-performance aerospace technologies in better understanding challenges at stake. Thank you very much for your attention.